Hello everybody, we are back for chain rule day 2. Okay, so the last time we were together we talked about just the chain rule in general, that if you have a composite function, or what I like to call a mother function, you have a function inside of another function, so when we take the derivative of that, we take the derivative of the outer function, or the mother function, leaving the baby, or the u, or the cloud, or whatever you want to call it, intact, and then we tack on the derivative of the inner function. Today, what I want to look at is what happens when we are beyond what I call a basic chain rule function, and the chain rule shows up in a little bit more of a complicated way. So, keeping it cartoony, what if instead of mother function with a turtle baby, we had something like this? Now think about mathematically what this would be. If you've never seen these, I believe they're called Russian nesting dolls. They're all kind of the same. Well, I guess they're not. They're at least slightly different. But there's one inside of another, inside of another, inside of another. This appears to be a set of 4, right? So there's this little wee one, and then she's inside. If you put this lid on here, she goes in, and then there's a bigger one, and then a bigger one, and then a bigger one. It looks like at least a set of 5. Apparently, I don't know how to count today. Okay, so we can have this in function form as well, right? We can have a function, a composite function that is a composite of 3 functions, or 4 functions, or 5 functions. And if that's the case, chain ruling once isn't going to cut it. If you have a composite of 3 functions, you're going to have to do the chain rule twice. So I want to look at some of those today. In the last video we talked about how to know when to chain rule, and this is more of a conversation about how to know when to quit. So do you chain rule once? Do you chain rule twice? Do you chain rule 3 times? How do you know when you're done chain ruling? When you have a situation like this, that can sometimes be a little tricky. So that's what we're going to focus on today. Okay, so take a look at this function I have here. We have the sine of the square root of x cubed plus 3. So we have the sine of a cloud, right? We've got a cloud here. We've got a baby, right? The baby, though, is itself a composite function. So I have the sine of my cloud, but if you look carefully at your cloud, it has a cloud in it as well. So when we were learning rules like the quotient rule and the product rule, we learned the product rule and we did it. Then we learned the quotient rule and then we did it. And we talked about, okay, well, what if I have product and there's a quotient in there? What if one of my factors in my product is a quotient? And we said, well, by any means necessary, right? If you are taking the derivative of a product and one of the things happens to be a quotient, then when you take its derivative, you use the quotient rule. So you're trying to use the product rule, but boom, suddenly you're using the quotient rule inside of the product rule, right? That happens. Same thing happens with the chain rule, right? If I have the sine of a cloud, the chain rule says that derivative is going to be the cosine of the cloud, derivative of the cloud. Now, what you have to do to get the derivative of the cloud, who knows? It could be that when you go to take the derivative of the cloud, you have a chain rule in there, another chain rule. You could have a product in there. This could be the sine of a product, or the cosine, or the sine of a quotient, right? We've already seen the sine of a sum or a difference. So we could have all of these rules kind of shoved together. In this case, what we have is a cloud that has another cloud in it. In other words, it's a chain rule, and when you go to take the derivative of the blue cloud in this case, you have a function that has another cloud. So we're going to also have to take the derivative of that pink cloud. And I'll show you what I mean here in a moment. But this is the kind of general concept that sometimes chain ruling once isn't going to be enough. As we see all these rules just kind of squish together. It's exciting. Okay, so let's take a look at this function. I rewrote it down here as the derivative of the sine of, instead of square root of x cubed plus 3, x cubed plus 3 to the 1/2. Okay, so I need the sine of, I have the sine of a cloud. My derivative is going to be the cosine of that cloud, and then I'm multiplying by the derivative of that cloud. Okay, so this is where the chain really becomes obvious. So I have the cosine of x cubed plus 3 to the 1/2. All right. Now I need to take the derivative of x cubed plus 3 to the 1/2. If I take the, in other words, act like this here is a whole new problem. I just need to take the derivative of that. Okay, well, when I take the derivative of that, it becomes 1/2 x cubed plus 3 to the negative 1/2, but there's a chain here as well. So I have to take the derivative of what is inside there. So I have cosine of cloud, fine. I'm sorry, the derivative of the sine of cloud, I have is the cosine of cloud. And then when I go to take the derivative of my cloud, that's this whole thing. This is your cloud prime. In order to get cloud prime, you had to chain rule. So you got a big, long answer here, right? I've got a 3/2, an x squared, and a square root of x cubed plus 3 in the denominator. This is a really fun function. If you rewrite this, you have a cosine of x cubed plus 3 to the 1/2. You have a 3x squared up top. You have a 2 and a square root of x cubed plus 3 in the bottom. It's an interesting looking function. Okay, here's another one. When you first look at this, hopefully you see your cloud or your baby, whatever you want to call it. So I have the tangent of this thing. Okay, so we're going to start off by just simply saying that I know that the tangent, the derivative of the tangent of a cloud is the secant squared of that cloud, and then I need cloud prime. Okay, so cloud prime, that's going to be the derivative of this, of 5 minus sine 2x. Okay, so I've got the secant squared of 5 minus sine 2x, and then I need to take the derivative of 5 minus sine 2x. So that would be 0 minus derivative of sine is cosine 2x, but this cosine in itself, it's the sine of 2x, not just the sine of x. So the sine of 2x becomes the cosine of 2x times 2. So notice here, again, derivative of tangent is secant squared. This piece comes down completely untouched. I take the derivative of this piece, and the derivative of this piece just happens to also be a chain rule derivative. So if I write this out again, it would be, I would write negative 2 cosine 2x times the secant squared of 5 minus sine 2x. And there we have it. 2 chain rules. Before you look at this and get overwhelmed or try to punch me through your screen, just look at it and look for that mother function. Okay. When I look at this, all I see is a cloud to the 5th. That's all I see. And I know the derivative of cloud to the 5th. I do. Where is my pen? I know what the derivative of cloud to the 5th is. I don't know where my pen is. It is 5 cloud to the 4th. That is the derivative of cloud, of course. I would never forget the baby. It's madness. So when I do the derivative of my cloud, I've got some stuff, right? But I'm starting with 5 cloud to the 4th times the derivative of cloud. So the first part of my derivative is 5 cosine, I'm going to write it, like this. 5x squared minus 3 to the 1/3, right? All to the 4th power. Now I need to take the derivative of this. Okay, well, if I want to take the derivative of the cosine of something, that's the negative sign of that something. Chain rule times the something, right? So the derivative of the cosine of this is the negative sign of that times the derivative of it. I'm going to go down here, which is 1/2 5x squared minus 3 to the negative 1/2. And oh my gosh, I still have a cloud because this wasn't just x to the 1/2, it was a quantity to the 1/2. So I have a third chain to do. I still have to do the derivative of the inside of that, which is 10x. Okay, so look at this. I have, if you look back at this original function, don't look at that. Okay, I have a 5x squared minus 3, which is a cloud, inside of a cube root function, which is a cloud, inside of a cosine function, which is the original cloud. In other words, I have a cosine function, and inside that is a cube root function, and inside that is a quadratic function. See what I'm talking about when I say like the nesting dolls, right? So I have this 5th order function. Inside of that is a cosine function. Inside of that is a cubic or cube root function, and inside of that is a quadratic. And when we do the chain rule, we work from the outside in. So we go 5 times my cosine function to the 4th, derivative of my cosine function, which is the negative sign. Then we go in one more step, take the derivative of that square root function that was in, or I'm sorry, that cube root function. I turned it into a square root, didn't I? Oh my goodness. Probably sitting there thinking, lady, this is a 1/3, which makes this a 1/3, and a 1/3, and a minus 2/3. Sorry about that. Let me start again. I have this whole big thing to the 5th, so I'm going to start from the outside in. So I have 5 cosine function to the 4th. Take the derivative of my cosine function. That becomes negative sign of my cubic function. Take the derivative of my cube root function, and that becomes a 1/3 quadratic function to the negative 2/3. Then I take the derivative of my quadratic function. And this is what I'm talking about, how to know when to quit. It's hard to know when to quit. Okay? You quit when you are out of clouds. You quit when you no longer have a function inside of a function. So if you look at this, in the beginning we have parentheses 5, there's stuff to the 4th. My Brian Passwater, the calculus love of my life, literally calls it stuff. What I call a cloud, he calls it stuff. Because it doesn't matter what it is. Take the derivative of it, right? So you have 5 stuff to the 4th. You got to take the derivative of your stuff. Well, it just so happens that your stuff is the cosine of even more stuff. So you do the derivative of cosine, you get negative sign of that stuff. Well, now I got to take the derivative of this stuff. Well, that's 1/3 new stuff, even more stuff, to the negative 2/3. Take the derivative of that stuff, and notice I no longer have like a function inside of a function. I don't have stuff anymore. I don't have a cloud anymore. At each one of these levels, if you look at them, you can see a cloud in there, right? Here, when you get to 10x, there's no more cloud. That's when you know when to stop. What you don't want to do is just keep on trucking. If you do that, you'll probably end up with every derivative you have equaling 0, right? And I've seen kids do this because they're like, chain rule, chain rule, chain rule, chain rule. And they go, the end, they get to the 10x, and then they're like, times 10 times 0. Oh, oops. You go times 10, because the derivative of 10x is 10, and then the derivative of 10 is 0, and then the whole answer is 0. Well, that doesn't seem right. So you have to know when to quit. Don't do this. As soon as you're out of stuff, as soon as you no longer have something inside of something else, as soon as you're no longer looking at a composite function, done chain rolling. Put your pencil down, or your mouse, or whatever the case may be. Maybe. All right, let's take a look at another one. Okay. These ones are tricky. They're tricky for me because I have a very hard time picturing. The first thing I do when I see something like this is I rewrite it. This means the sine of 3x plus 1 to the 5th power. So the first thing I'm going to do when I see something like this is write it like that. The sine of 3x plus 1 to the 5th power. And then for me, it's much easier to see that I have a chain rule situation, right? So I have a cloud to the 5th, and when you look at your cloud itself is a chain rule piece, okay? So let's do it. Let's go from the outside and work our way in. So if I do f prime of x here, that's going to be 5 times this stuff to the 4th. Now, we have to take the derivative of this. The derivative of the sine of something is the cosine of that something. And couldn't have just been an x. It had to be the cosine of something else, another cloud. So I'm going to take the derivative of that. And there's my derivative. So it's 2 chains in this case. So I have something to the 5th as my first function, and then I have the sine of something else. It's my second composite. So I have a function inside of a function inside of a function. So notice I had to chain rule twice. I have a linear inside of a sine inside of a 5th order. It's a composite of 3 functions. I have to chain rule twice. Okay, let's look at a couple more examples, and then I promise I'll leave you alone for now. Okay, I have the secant cubed of 5x plus 2. So again, I am going to rewrite this as the secant of 5x plus 2 to the 3rd power. You do not have to do this. I know a lot of people are completely able to just visually move that 3 up there and be fine. I'm not. I mess it up every time, so I always rewrite it. Okay, so if I want my derivative, again, let's start from the outside in. So I have a cloud raised to the 3rd power. So 3, my cloud, untouched of course, raised to the 2nd. And then I need to take the derivative of this. The derivative of the secant of what is a new cloud, secant of 5x plus 2, is the secant of 5x plus 2 tangent of 5x plus 2. And then of course, again, you have these. Remember, you only do it once. Times 5. So even though it's written twice, this is one derivative. The derivative of secant is secant tangent, chain rule at one time. So times 5, just one time. And again, count how many functions you have here. I have a function, in a function, in a function. I have a linear, in a secant, in a cubic. 3 nested functions, 2 chain rules. All right, last one. Okay, look what's happening here. I have a quotient rule, and when I'm doing the quotient rule, I'm just going to happen to need a chain rule along the way. What are you going to do? Okay, so let's get our g prime of x, and let's set up our quotient rule. I'm going to need an x minus 7 to the 24th on the bottom. That's my denominator squared. So on top, I need an x minus 7 to the 12th, so denominator. Derivative of numerator. The derivative of my numerator is going to require a chain rule. I have the sine of x cubed, so I need the cosine of x cubed, chain rule, times 3x squared, minus my numerator times the derivative of my denominator, which is 12, x minus 7 to the 11th, and I need a chain rule, but good news, the derivative of x minus 7 is just 1, so even if you forgot to chain rule, you would be forgiven in that case. Just FYI, if the chain rule piece is a 1, you are not by any means required to write it. If the chain rule piece is a 1, you don't have to report that. I'm rewriting this because I want to show you. Again, in multiple choice, you have to be careful. Because in multiple choice, they could cancel out 11 of these x minus 7 quantities. So that's just something to watch for. If you are asked to simplify, look, there's 11 of them here, so that would knock out all but 1 there, and you'd be left with 13 down here. Right, so you have 11, x minus 7 to the 11th in common there, so you can factor 11 of them out and cancel. Other than that, I don't believe there's any simplification to be made. Okay, so this is kind of how the chain rule just gets a little more dicey, where you have it mixed in with other rules and frankly mixed in with itself. Function and a function and a function. The key to knowing when to quit, again, is looking at how many functions you have nested, and it's always 1 fewer than that. So if you have 5 functions, if you have a function and a function and a function and a function and a function, you're going to be chain ruling 4 times. Okay. So if you're having trouble with knowing when to quit, that's a good way to look at it. Just kind of work from the inside out, count how many functions you have. You should be chain ruling one fewer time than that. All right, this is the chain rule, what I call the chain rule in practice. So I'm taking actual functions, taking their derivatives, and the chain rule pops up for me. The next thing that we need to look at is what the AP is a huge fan of, which is kind of the chain rule in theory, right? So they don't give us a function, but they talk to us theoretically about functions, and we have to make sure that we incorporate the chain rule. So they might define a function like, I have this function h, and guess what? It's f of g of x. And we don't know what f is, and we don't know what g is, but I'll bet you we know that needs chain ruled when we take its derivative. So in the next segment, we'll call it, we're going to talk about how the chain rule can come at us more abstractly or theoretically. Okay? I look forward to it, and I'm sure you do too. Okay. See you soon.